Hello everyone, and welcome to the Virtual Technology Summit. My name is Liron, and we'll spend the next hour talking about the session, The Optimizer Complexity is Great, but. This is a general safe harbor statement that Oracle used in the presentation. Take a minute to read that. It basically says that this presentation doesn't contain any commitments, and you should not rely on the information from this presentation when you make a purchasing decision. So read that quickly, and we can start. Before we start, let me introduce myself. My name is Liron Amitzi. I've been an Oracle DBA for about 18 years now, and a database consultant for about 14 years now. I worked with lots of aspects in Oracle databases, and I mainly specialize in database configuration, architecture, troubleshooting, high availability, and tuning. I've been an Oracle Ace since 2009. I'm originally from Israel, and I recently moved to Vancouver, Canada. I'm a co-owner of Brillix, a professional services and consulting company in Israel, and I will talk about Brillix in the next slide for you. I'm very involved in the Oracle user group community. In Israel, before I left, I was involved in ILOG, the Israeli Oracle user group, and in the last 5 years there, I was a board member. And here in Canada, I am part of the executive committee of BCOUG, which is the British Columbia Oracle user group. BCOUG is basically a consolidation of Victoria Oracle user group and Vancouver Oracle user group. A little bit about Brillix. Brillix is a consulting, services, education, and software company in Israel, as I said. We are in the process of opening a branch here in Canada for North America, and our main specialization are database and security. We have a team of database experts, and we provide professional services, consulting, and run projects in database architecture, installation, performance, troubleshooting, and basically everything that there is in the database area. And we do that for Oracle databases and other databases as well, SQL Server, MySQL, DB2, and other relational databases, as well as NoSQL and big data solutions. In the security team, we have experience in implementing Oracle IDM, Access Manager projects, and other security tools. And we also develop software, mainly in the area of database security and database management. In Brillix, we have 4 Oracle Aces, 1 Oracle Ace Director, 2 Oracle Aces, I'm one of them, and 1 Oracle Ace Associate. So about the session today. As I said, the title of the session is The Optimizer Complexity is Great, but. So I'm going to talk about the optimizer, but it's not going to be a regular session about the optimizer abilities. It's going to be a session about certain aspects of the optimizer behavior and how it affects us as DBAs. I'm going to talk a little bit about the optimizer, a very general overview. Then I'm going to talk about static optimization and dynamic optimization. If you don't know what these terms mean, that's perfectly fine because I actually made them up. I couldn't find any terms for what I'm going to talk about. So these are the names I gave to these behaviors and features. So I'm going to explain what I mean by static optimization and dynamic optimization. I'll also talk about specific features relevant to the static and dynamic optimization. And at the end, I'll talk about how this affects us and about improving our skills with these relatively new optimizer behaviors. It all started a couple of years ago. I was a consultant, and one of my clients was complaining about some performance problem he had with the report. So I went to him, and in the meeting we had in the morning, he explained that they wrote a certain SQL. It was a quite complex SQL for one of the reports. And the performance of the report was quite weird. When they executed the report a few times straight, one execution after the other, the odd executions, the first one, the third one, the fifth one, and so on, were slow, and the even execution, the second execution, the fourth one, and the sixth one, and so on, were fast. And they didn't change anything in between the executions. So it was quite strange, and I was thinking to myself that they probably missed something, because Oracle usually doesn't behave that way. and I didn't understand what's going on. So I asked them to show it to me, because I was sure that once I sit there and they show what they do, I would understand what they missed or what they do that causes this weird behavior. So I sat there and they showed me the executions of the report, and they actually only pressed the button to get the report results, and then just pressed it again to get the results again, and again and again. And oddly enough, it was exactly how they described it. So I needed to understand what was going on there. So what might cause such a strange behavior, and how can we debug issues like that? And I sat there and I tried to understand if this is an Oracle issue or optimizer issue, or maybe the server is overloaded or something else that can affect the performance, like the I/O subsystem or the network, or any other things that have any effect on the system or the database or even the client-side report system. And it was so consistent and so precise that the first execution was slow, the second was fast, and the third was slow, and the fourth was fast, and so on. And it happened all the time, and it happened exactly at the same order. So it didn't make any sense that it's something outside of the database. It's probably something in the database, but I still needed to understand what it is and why Oracle behaves like that, and how I can even debug this to understand this strange situation. So I'll get back to this story and answer the question at the end of the presentation. Let's do a short overview of the optimizer. I guess most of you know the optimizer quite well. It is definitely one of the most complex pieces of code in Oracle, but we can sum up its role quite simply. The optimizer only role is to decide how to execute an SQL query and generate an execution plan for it. It has to generate the most efficient plan, so the SQL will run as fast and efficient as possible. But it also has to do it very quickly, because execution time is highly important and we don't want to spend too much time on the optimization process itself. The optimizer uses all kinds of information to do its job. Some of it is static information, such as statistics, and I will talk about it in the next few slides. But relatively recently, Oracle is making the optimizer more dynamic. This makes the optimizer much more sophisticated by allowing it to be aware of other information than the static one we've already got. Oracle collects information just before or during the execution of an SQL statement, and then can change the optimizer's decisions. So the optimizer is much better, but it makes our lives as DBAs much harder. As I said at the beginning, static optimization is not a standard term. It's only something I decided to use because I couldn't find any better term to explain this behavior and features. Static information that the optimizer uses for its process has existed since the cost-based optimizer was introduced in Oracle 7. This is the optimizer way to get information about the objects and other things that are relevant for the query, so it will be able to get better decisions and generate a better plan. In this static information, I include object statistics, system statistics, histograms, table structure, object existence, such as indexes and material as views. I also include here information the optimizer understands from the query, such as columns, data types, predicates, and so on. Besides that, the optimizer uses a lot of math calculations to estimate the cardinality and cost and decide on the final plan. Today, Oracle is still improving the static information in two ways. One is improving the way it gathers the information, making it more efficient and even automatic. The other way is improve the quality of the information, like gathering more information with more detail. This improves the ability of the optimizer to make better and more accurate calculations, which lead to better plans. Now that we understand what I mean by static optimization, let's see several features in this area. In Oracle 10G Release 2, Oracle changed the way that Create Index gathers statistics. Before Oracle 10G Release 2, after we created an index, we had to manually gather statistics on it, or add a clause to the create index command to gather the statistics during the create index operation. Starting with Oracle 10G Release 2, Oracle automatically gathered statistics when it creates an index. This might sound as a small feature, but it is important to talk about it, because the command behavior is changed. And if we count on a certain command to do a certain operation, and this command changes, things will suddenly work differently for us, and we won't understand why. In Oracle 11G Release 1, Oracle introduced the extended statistics feature. Before Oracle 11G Release 1, the optimizer didn't have information on relations between columns in a table or output of expressions, such as functions. If columns had relations between them and we added the predicate on these columns or on an output of a function, the optimizer couldn't estimate the cardinality correctly, simply because it didn't have the information. And that sometimes led to a bad plan. With extended statistics, we can gather statistics on group of columns or output of expressions, so the optimizer will have this information when it generates the plan. Another feature of 11G Release 1 is synopsis. This is relevant mainly for partition tables. When we have a partition table with many large partitions, in order to calculate the number of distinct values of a column, we need to scan the entire table. Even if we added data to only one partition, we still have to scan the entire table to get the correct number of distinct values for a certain column. With very large tables, this was a too heavy operation, and sometimes DBA simply accepted the fact that the number of distinct values of a table is incorrect, and that obviously affects the optimization process. With synopsis, when we add or change data in one partition, we only need to scan it, and Oracle can find the correct number of distinct values for the entire table correctly. In Oracle 12c, Oracle added new histogram structures. Before 12c, we had the frequency and height balance histograms. These two histograms have limitations in some cases. Sometimes the number of buckets wasn't enough, or in some cases the cardinality estimation for certain values wasn't accurate enough. In Oracle 12c, we have two new histogram structures, top frequency and hybrid, which overcome some of these limitations and allow the optimizer to estimate the right cardinality in more cases. We talked about static optimization in the last couple of slides, and the idea behind it is quite simple. The optimizer gets all the information, makes calculations, and generates a plan. Once the plan exists, it is saved in the shared pool and is used when executing the query. But the static optimization is still limited. When the optimizer generates a plan, in some extreme cases or complex scenarios or complex SQL queries, the cardinality that the optimizer calculates is simply wrong. And if the cardinality is wrong, sometimes the plan is not very efficient. Dynamic optimization, on the other hand, is totally different, let's say, mechanism. Again, this is a term that I made up, and it describes a new set of features that allow the optimizer to work in a different way. It's not only calculation, but operations that happen just before an execution, during an execution, or right after it, and they affect the optimization process. These operations can affect the running query immediately or the future executions of the query. I called it dynamic optimization since it relies on dynamic data. The things that affect the optimization process are data from an actual execution of an SQL, the current load of the database, or other dynamic data. So it is much more dynamic and related to the actual activity and real data from the database. I split the features of dynamic optimization into two groups. The first one is pre-execution features, and I chose to talk about three important features here. And as you can see, they are generally newer than the static optimization feature I showed before. The first one is adaptive cursor sharing, and it was introduced in Oracle 11G Release 2. Before 11G Release 2, when we used bind variables in a query, the optimizer generated a plan, it was saved in the shared pool, and Oracle used it when executing the query. With the first execution, Oracle used bind picking to check the values and generate the plan according to these values, these bind variable values. But once the plan was generated, in the following executions, it didn't matter which values I had in the bind variables. Oracle used the same plan. Oracle realized that the same plan is not necessarily good for different bind variable values. So with adaptive cursor sharing, when I execute the same query for the second time with different bind variable values, the optimizer can estimate if the existing plan is good for the new bind variable values as well. If it looks good, the optimizer will use the existing plan, but the optimizer can also decide that with the new values, there will be a totally different number of rows, and the existing plan will not be good enough. In these cases, it will generate a new plan for the same query. So eventually, for a single SQL, we can have several plans in the shared pool for different sets of bind variable values. So again, if we counted on an SQL with bind variables to have a single plan, and with any set of bind variable values, the same plan will be used, from 11G Release 2, this is not always the case. The next feature is automatic degree of parallelism. If we are using parallel execution, and we use this feature, Oracle will automatically choose the degree of parallelism for each query. It will take into consideration the resources of the machine, such as number of CPUs and the system load. It also allows something called statement queuing. With this feature, when the query needs a certain degree of parallelism, and there are not enough parallel processes available, Oracle can decide to queue this statement. So the statement is paused, and it will wait until enough resources become available. Once enough parallel processes are available, the statement will start running. If I'm using this feature, again, this is a change in the behavior. A parallel query will not necessarily start to run immediately. It might be queued instead of running in serial when not enough resources are available. And also, I cannot control the degree of parallelism that Oracle chooses. It just chooses automatically a degree of parallelism for every query. The last feature I'm going to talk about this slide is dynamic statistics. And that's the new name for dynamic sampling, which was introduced in Oracle 9. In Oracle 12c, they changed the name, and it's basically the same feature with one addition. So dynamic sampling is the ability of the optimizer to sample the data of the table just before it generates a plan for a query. It does it very quickly to try to understand the data of the tables in order to get more accurate estimations. In earlier versions, the data it sampled and the cases it used dynamic sampling are controlled by the parameter optimizer dynamic sampling. The values vary between 0, where dynamic sampling is turned off, and 10, where dynamic sampling happens more often and gathers more information. In any case, the information that was gathered was temporary and was used only for the specific SQL query. In 12c, the parameter name is still the same name, but a new value was added, the value 11. So now the values are 0 to 10, which is the same as before, or 11. And this value means that the optimizer chooses by itself when to use dynamic sampling and what data to sample. But another big difference is that the information gathered by the dynamic sampling, which is now called dynamic statistics, is saved in memory and can be used for other queries as well. The second group of features I'm going to talk about are during or post-execution features. With these features, the optimizer can realize or understand things during the execution or after the execution, and then act accordingly. The first feature is cardinality feedback, and it was introduced in Oracle 11g Release 2. The idea behind this feature is that once the optimizer generates the plan, it knows the calculated cardinality of every line in the execution plan. It uses the cardinality to decide which access path or join methods to use in order to generate the most efficient plan. But as I said, sometimes it gets the cardinality wrong. It can be because of a complex scenario or a complex query, or it doesn't have enough information, or other things that prevent it to do the calculation correctly. Oracle realized that in some cases they cannot make the optimizer get the right cardinality. So with this feature, once the query is executed, Oracle compares the number of rows it actually got from each line of the plan with the optimizer estimation. If these numbers, the expected cardinality from the optimizer and the actual cardinality for the specific line during the execution, if these numbers are very different, and this means that the optimizer was wrong with its calculations, Oracle will give a feedback about that. So it will save the information about the correct cardinality and turn on a kind of a flag for the next time. Once the SQL is executed again, the optimizer knows that there is a cardinality feedback, which means that the calculations were wrong in the first place, and it will use this information to generate a new plan that will be hopefully better. The second feature, adaptive plan, is a 12c feature, and this is taking the cardinality feedback one step forward. So if during the execution of a query, Oracle realizes that the actual cardinality is totally different than the optimizer calculated cardinality, it can change the plan on the fly in the middle of the execution. The common example for this is a case when the optimizer estimates it will get a few rows from one table to join with another table. So it decides to use nested loops as the join method. If in the middle of the execution it gets many rows from the first table, it can change the plan on the fly during the execution to do a hash join, which is much more efficient in these cases. We need to understand that with these two features, once we executed a query and we check its plan, it's not necessarily the plan that will be used in the next execution of this query, and it might not even stay the plan for the entire first execution. If the estimated cardinality is totally wrong, the plan can change, and the plan we saw at the beginning of the execution might not be relevant anymore. So what's wrong with that? These features look really great, and they help improving the overall performance of our database. The problem is that with dynamic optimization, the optimizer is much less deterministic. Now, I'm a computer geek, and I like things to be deterministic, but the optimizer is not anymore. In the past, if I gave the optimizer a query with specific static information, I knew it would get the plan I expected it to get. It was easier to reproduce problems in test environments. I could see plans and tune them, and I knew how changes I do will affect the production because I tested them in other environments. Now, with all the dynamic optimization features, the first execution might cause cardinality feedback, so the plan will change. Or the plan will change during the execution itself, if this is Oracle 12c. The plan can change with different bind variable values, and there are many other things that can change the plan all the time. It is also changing in different ways in different environments, so it's much harder for us to predict how things will work on the production or in the future. We cannot rely on the SQL plan that we see, and we can't simply copy the data and the statistics and reproduce the problem in the development. So our work is getting much, much more difficult. So what do we do now? We understood the problem, and now our jobs as DBAs is much more complex, and we need to get to know how to handle these situations. First of all, we don't only need to understand what the optimizer does, we need to know what can affect the execution plan. And now, with these dynamic optimization features, there are many things that can affect the plan. Some of them will affect the plan only in the second time, or only in the middle of the execution. Some will cause queries to wait for resources. So the plans and the performance can change dynamically all the time. In my opinion, the most important thing is to know as much as we can about the optimizer features and behaviors. Because once we see a strange optimizer behavior, it is very important to understand that there are features that might be relevant for this behavior. If we don't know these features, it is much more difficult to understand what's going on with the optimizer and why it behaves like that. I saw that in the past when I went to clients and they sometimes didn't realize that the database is using a new feature or behaves differently than before, and they didn't understand why, simply because they were not aware of these features. So it is very important to know as many features as we can. All the new features. We don't need to understand them completely. We just need to know that they exist and understand the basics of these features just to realize that they are related to something that we see. And one last thing. If you do that today, and you definitely shouldn't, don't trust an offline execution plan. Don't simply generate a plan, look at it, decide to change some stuff, and then generate the plan again, say, okay, it looks okay now, and implement it in production. It just doesn't work that way anymore. You should check the real execution plan that is used, and if you tune a query, you should verify that the correct plan doesn't change in time. First of all, how do we know if Oracle uses these features? So when we look at the execution plan, just after the table with the execution plan itself, there is a part with the title Note. Sometimes we just ignore this part or don't look at it at all, but it is very important because in this part, Oracle says if it uses certain features. So these are examples of this part in the execution plan. The first line here shows that cardinality feedback used for this statement. So we know that for this execution plan, cardinality feedback was used. And even if we don't know what cardinality feedback is, at that point, when we see this line, we can go to the documentation and check what cardinality feedback is. And it is very important because it affects our execution plan. The second line is, this is an adaptive plan. Exactly the same, but for adaptive plans and not cardinality feedback. And the third line is dynamic statistics used, dynamic sampling level 5. So this part of the execution plan tells quite a lot about what the optimizer used during the execution plan generation, and it is very important just to give it a glance to see if there is something important. And if there is something we don't know, we should go and read about it a little bit, just to verify that it is not something we need to handle. Here is a useful tool. Actually, it's a very useful tool when we tune a query or troubleshoot a problematic execution plan. This is the hint called Gather Plan Statistics, and I like it a lot and used it quite often lately. This hint tells Oracle to gather information about the estimated cardinality and the actual cardinality. It has some overhead because it collects extra information during the execution, but it is very, very useful. So if after the presentation this is the only thing you remember, I'm perfectly fine with that. If you want to learn a little bit more about it, just open Google and search for Gather Plan Statistics. There is a very good article in Oracle Optimizer blog written by Maria Colgan, and it is an interesting article with explanations and examples. So when you add the gather plan statistics hint to a query and run the query, it captures information about the estimated and actual cardinality. And then you can use the DBMS explan.display cursor. Don't forget the format parameter. It should be all stats last for the last query. And then you get the table with the execution plan. But in this table, you get another new column. And this column is the actual number of rows returned from each line of the execution plan. It is very, very easy to compare the estimated and the actual cardinality and find the differences. Now we can understand why the optimizer estimation was different from the actual number. And this is a very good place to start when investigating an optimizer's strange behavior or general SQL tuning or execution plan problem. The next one, the display cursor with the format adaptive, will show the adaptive plan information. The adaptive plan, as you remember, is when Oracle can change the plan in the middle of the execution. So with this format, the adaptive, we will get all the lines of the execution plan, including the lines from the original plan that were, let's say, deleted from the plan, or the lines that were changed. So in the same table of the execution plan, we can understand what the original plan was and where it got changed. If you work with Oracle 12c, this is the way to see the change in plan, so we can tune the query or understand how to fix it. Another thing that is very useful is data dictionary views, of course. I wrote here only 4 VDollar views, but every feature has information about it somewhere in the data dictionary. For the adaptive cursor sharing, we have 2 columns in VDollar SQL view. The columns are is-bind sensitive and is-bind aware. If we query a specific SQL from VDollar SQL, we will see that is-bind sensitive and is-bind aware are true or false to understand if adaptive cursor sharing was used for this SQL or not. Dynamic statistics, it's not very straightforward, but that's how Oracle did that. In VDollar SQL plan, we have a column called Other XML, and inside the XML structure, we can see if dynamic statistics or dynamic sampling in older versions was used or not. For cardinality feedback, in VDollar SQL shared cursor, we can see the use feedback stats column, and that will indicate if cardinality feedback was used or not for this specific SQL. And for statement queuing in automatic degree of parallelism, there is a status column in VDollar SQL monitor. The status value will be queued for statements that are waiting for resources to become available. So let's go back to the story from the beginning of the presentation, where I had this report that the first execution was bad, the second was good, the third one was bad again, and so on. In order to understand what's happening, I simply sat there and thought. As I said, it did look like a database problem, and I needed to understand what can change performance like that. The thing that came to my mind was cardinality feedback. And to prove that, I generated the plans, both when the report was running slow and when it was running fast. And I saw the note section after the execution plan. I also checked VDollar views to see the different plans, and it actually was cardinality feedback issue. It still didn't explain the whole story, but as I was digging deeper, I started to understand it. In the first execution, the optimizer got wrong cardinality for one of the lines in the execution plan. So what happened is that Oracle realized that during the execution, and it turned on cardinality feedback for the query. When we executed the query once again, Oracle realized that there is a cardinality feedback issue here, and the optimizer kicked in to generate a new plan. It used the feedback it got from the previous execution, so it generated, obviously, a different plan. And actually, it was much a better plan. As we saw, the second execution was faster. So we see that the feature works, and the second execution was actually faster. And this is actually the strength of these dynamic optimization features of Oracle. The problem, specifically in this case, was that this feature, in conjunction with Oracle bug, caused the optimizer to flip between two plans. And I actually talked about it with the optimizer guys at the Oracle Open World after I had this problem. So the thing was that the second plan, which was much better, also had a cardinality issue. Again, the optimizer miscalculated cardinality in one of the lines of the execution plan. And then Oracle used cardinality feedback for the second plan as well. Once we executed the query for the third time, Oracle saw that there is cardinality feedback issue again. So the optimizer kicked in again to generate a better plan. But strangely enough, with the cardinality feedback from the second plan, the optimizer got back to the first execution plan, which was the bad execution plan. And that is actually related to the bug that was in the earlier versions of Oracle 11G Release 2. So the third execution had the same plan as the first execution, which was bad. So it was slow again. But again, the cardinality was wrong. So Oracle used cardinality feedback once more. And the fourth execution was the same as the second one, which was the good plan. So all the odd executions were slow and the even executions were fast, simply because it flipped between these two plans. And actually, it stabilized after 10 executions, because Oracle does not allow using the cardinality feedback feature more than 10 times. But still, that was the problem, and that was why the performance changed between odd and even executions. In this case, once we realized that this was the problem, the solution was not that difficult. We simply fixed the statistics. I have to admit that I don't remember exactly if we gathered new statistics on one of the tables or added histograms or something similar. But once we fixed that, the optimizer cardinality estimation was close enough to the actual cardinality. So cardinality feedback didn't happen, and that completely fixed the problem. So as you can see, the problem here was to understand the problem and not fixing it. Once we realized that the problem is cardinality feedback, the fix was quite simple. But my job as a DBA was much harder in understanding what caused this problem, what feature, and find the bug, and then, only then, I could fix the problem. So let's summarize. The optimizer is getting much more dynamic and allows better tuning options and better execution plan generation. But our job as DBA changes as well. From tuning a query using all the information we have to understanding what the hell is going on. Because the optimizer is more dynamic, it is less deterministic, it changes behavior on the fly, it gets all kind of weird behavior, and now we need to realize what happened and why, and how to fix it. So today, more than ever, we need to identify the actual plan that was used, because it can change all the time. It's not static anymore as it used to be. And again, we need to be very aware of these features. If we understand these features and know them, even a little bit, we can understand how the optimizer changes the plan during the lifetime of the database, and we can diagnose and fix problems much easier. Thank you for listening. I hope you enjoyed the session. We have about 20 minutes for Q&A, and then you can move to the next session. These are the details if you want to contact me. I have a Twitter account and a blog. If you want to read or follow me, you are very welcome to do that. This slide will be shown in the next 20 minutes or so feel free to ask questions. Thank you very much.